Okay. So this is quiz 9. LeChateliers principle. And question number 1 gives you the reaction for ammonia is in equilibrium with 2 moles of ammonia. And so we asked, well, which way will it shift if we increase pressure? So we're going to increase pressure, which would be accompanied by a decrease in volume, Boyle's law, where pressure is proportional to 1 over V. Boyle's law is the only empirical law which is inverse. Charles' law, Gay-Lussac's law, Avogadro's laws are direct relationships between the gas law variables. If we apply an increase in pressure to this, we look at 4 molar volumes on the reactant side and 2 molar volumes on the product side. Let's see. Increase pressure, decrease volume, shifts reaction to lower Vm side of the reaction. See what I'm saying? So since we have 4 on the reactant side, 2 on the product side, we have a right shift. Now, if we had decreased the pressure and increased volume, it would shift the other way. Everybody hear me? Okay, so I'll make that note in here. Decrease pressure, increase volume, shifts reaction to the higher Vm side of reaction and equation if you want to be picky about it. So is very, very let's do it this way. Effects change in pressure, change in volume on equilibrium containing solids or liquids. If I have an equation, if we change the pressure volume conditions on this, the issue still applies relative to the gas. But the trick is you ignore solids and liquids. The issue is, what is the molar volume of sugar, solid? It's 0. There ain't no gas. What's the molar volume here? It is, regardless of the 2, it's still 0. 2 zeros is still 0. Only component in here that demonstrates molar volume is the CO2, and delta Vm of this one is 2. So if we evaluate the reaction in terms of numbers of molar volumes on the reactant side and the number of molar volumes on the product side, we find that the product side has a larger number of molar volumes. So this is the high side. So we call this, for instructional purposes, the low Vm side, and the product side in this case, the high Vm side. So from this, the rule continues to apply. If you increase pressure, it's going to condense. It's going to shift to the low side. If you decrease pressure, it's going to function to shift to the high side. So a decrease pressure, increase volume, shifts toward the high side. Increase pressure, decrease volume, shifts toward low side, low Vm side, I should say. So you choose the conditions that you want to apply. That's the issue with LeChateliers' principle and synthesis. Last problem we worked the other day asked, well, what can you do to shift the reaction, make more product? Well, now you have a choice to make to apply it to the problem. Increase temperature, decrease temperature. Well, what does it do to the reaction based on the data that I gave you? Same here. If you want to decrease the CO2 yield in this thing, what would you do? You would increase pressure, which would force the reaction back to the reactant side, 0 molar volume side. Okay, you're given A plus 2B in equilibrium with AB subscript 2. If you mix in a reaction kettle container these quantities, will the reaction shift left? Will it shift right? Will it not shift? And how do you determine that? Here's my next. Miss Megan. How do you determine which way this is going to shift if you're given concentration? Okay, we want to know if it's going to shift right or shift left, or what will it do in order to reach equilibrium. So given data like this, to determine direction of shift, compare QC with KC. Now both are calculated the same way in terms of the mathematics. KC is equal to products over reactants in this context, and with this problem, and there. QC is also calculated based on the concentrations given. In this problem, you are already given the Kc value here at 0.025. On test day, I do put a problem on there where you will have to calculate K based on the data. And then I'll give you a second set of concentrations that you will calculate a Q value for and compare and determine which way it will shift based on the comparative. We'll show you. So we've got this, so we need to compare what the QC value is. QC is a condition that may or may not be in equilibrium. We don't know yet. So we assume it's not at equilibrium in the context of working this problem. So we have the concentrations given is 20 mole per liter, and A is 5 moles per liter, and B is 10 moles per liter, but we need to square that. And the outcome of this, I worked it out earlier, is a 0.04 value for the QC. To determine which way it shifts, I gave you a setup, so to speak, between K and Q, and recommended that you list the K 3 times. The symbology should be written down like this: KC, KC, KC. K comes before Q in the alphabet, so the first thing is the K. Then follow with QC, QC, and QC. I put the equals in the middle and insert inequalities. It doesn't matter. Just be sure they are opposite, like this. If you set this up in this context, the arrow points in the direction that the reaction will shift. The arrow inequality, this would be a right shift if these conditions were determined. If you determine QC equal to KC, you are at equilibrium already. Or if you determine QC to be greater than KC, which is the case that we have here, QC is greater, the arrow points to the left. And so this reaction would be a left shift right there. This is the important issue that you have to keep in mind. It's not difficult. And second thing, of course, you have to be able to compute and compare the Q and the K based on the data that's given to you. So we'll use a choice in this one. That looks like it might work. Which one will not shift? This was the issue that I wrote on the board and want you to appreciate. There's one equation in here that I definitely want you to pay attention to, because it is a curveball if you're not careful. This analysis depends on the principle that if in a chemical reaction at equilibrium, the sum of the molar volumes, gas values of the reactants is equal to the sum of the molar volumes of products. No reaction shift occurs. So looking at this collection, we see in the first case calcium carbonate, calcium oxide, and CO2. Well, the molar volumes in this case are just one molar volume on the product side. So increasing and changing pressures and volume will affect that reaction. This is the one I want you to pay close attention to, right here. It doesn't look like it's balanced. We're going to need a 2, I think, right here. Shame on me. Need a 2 right there. So that's 4, 4, 1, and 1. And then we have 2 and 2 is 4 on water. Leaving it off probably just made it obvious. But if you get a reaction like this, be sure you check the state of existence. This reaction shows up in one of two forms in the literature. I can write this. This is methane combustion. This is one way to write it, but you'll find these show up in this context. And the 2 look like a 2. See? See the difference that I'm trying to emphasize down here? In the second case, we have 2, 3 molar volumes here. 1, 2, 3. We also have 3 molar volumes over here. Application of increasing or decreasing pressure issues will not shift this second case. But changing pressures in this first case will, because the water on the end is in liquid form. That doesn't apply to the equal volumes, no shifts. So in this case, an increase in pressure, reactant shifts it to the low side. Decrease back to the left, to the high side. Check mark that. Yeah, I've seen this show up on MCATs and pharmacy school entrance exams and things like that, where the problem would revolve around you picking out or determining that this is an unchangeable equilibrium or not. And has a question. Let me see if I can blow it up a little bit. Literally. I get a zoom in. Which of the following equilibria would not be affected by a change in So we have 2 on the left, 2 on the right, no shift. C choice. Okay. The molar volume here is liquid. It ain't a gas. It creates no bubble, so to speak. This does. This does. That's not a solid, the gas.
Oh, okay, I see now.
We're not running it at minus 286 Kelvin. 2 VMs, and this one is 1 VM. So with 2, 3 against 1, it will shift right for an increase, shift left for a decrease.
All right.
In this case, this is the effects of changing temperature of a reaction system. In order to make a decision on how temperature changes will affect a reaction, you have to know whether it's endothermic or exothermic. And the notations that were given the other day for endothermic and exothermic reactions should be taken to heart. First, before you can even attempt this, you have to recognize endothermics reactions as those, by definitions, that gain energy from reactants to products. An exothermic reaction, by definition, releases or loses energy from reaction to product. And we've looked at this in several contexts over our time in here. One point in case was the transition state issue. When we talk about reaction progress as it moves from reaction to progress, we frequently illustrate that progress using what we call a transition state. If you're talking about an endothermic reaction, the products have to wind up higher than the reactants in a graphic display like this. When we talk about reactants, whatever they are on the reaction side, they inherently contain what we call a positional energy, potential energy. Positional or potential energy content. So really it's not a change, it's a content. I'm going to take the delta out of that right there. Potential energy content or positional energy. I frequently get in trouble with my colleagues for calling it that, but it works. In an endothermic process, let's say we call this one endothermic. What did I say? The products have to wind up above the reactants. I'm going to put the reactants here. So the heat content of the reactants is right there. When the reaction is completed, the products will be there, inherently above, obviously above the reactants. In getting from reactants to products, it will have to go through the transition point right here. And to this point, from the positional energy of the reactants to the activation energy point is the change is the delta EA for the forward reaction. Once you pass the activation point, it moves to wherever it's going to stabilize. In the case of this one, it wound up here, which, I'll move this out of the way. And so our heat content of the products is right there. I'll put energy here. So the energy of the products is a bigger number on the vertical scale than reactants, right? So if HP is bigger than HR, and I take the difference to get the delta H, I will be talking about, or I have calculated, what we call the delta H of the reaction, and it's greater than 0 in this case. When writing a reaction that is endothermic, you place the delta H of that reaction on the reactant side. A plus B plus delta H of reaction goes to AB in this format. So you see a number sitting there. Or you could go A plus B in equilibrium with AB, and delta H of the reaction is equal to, is a number greater than 0. Right there. So you will see both of these show up on exam day. Both of them are used. And we'll talk about shifting in a minute. Exothermic reactions are defined as those reactions which inherently lose energy transitioning from the reactant to the product side. That is, the products are at a lower positional energy than are the reactants. So if we start with our reactants right here, then the positional energy of the reactants is what we're talking about. And when the reaction is complete, we find the product's positional energy is right here. This is reactants, and this is products, sorry. If I take the products, which is a larger number, minus the lower number, I'm going to get a negative value, indicating a loss of energy. That's why it's very valuable to know how to interpret this diagram, and it's used extensively in future courses that you will take, especially organic chemistry. And when we talk about the EA positional energy of activation versus the the positional energy of the reactants, the distance between these is the delta H activation energy of the forward reaction. And from the positional energy point to the activation energy, we have a delta H A for the reverse reaction would be this distance. And find the delta H of reaction to be right here. Now, this is a double-edged sword in terms of working problems. If a problem asks you to calculate the heat of reaction, you would find out the total heat of the products and total heat content of the reaction, take the difference, and you would have delta H. It will come out negative. This will be, the value will be less than 0. On the other hand, if you're working a problem that tells you this reaction has a forward activation energy of such and such, and a reverse activation energy of such and such, what is the heat of reaction? Well, you have to add these two together to match this side here. So the heat of reaction, the activation energy plus the heat of reaction is equal to the heat of activation for the reverse reaction. Be careful. The reality of this number right there is, yeah, it's the amount of energy lost. But if you're going to solve a problem that wants to find out what the reverse energy is, you have a number here, you better add it to it. Don't subtract it. That can be confusing when you're working problems with this design. Say if you can see this, say this is 20. You can see that right there. And right here is 200 on this distance. You would have to 20 plus delta H of reaction. It's asking you for the delta H of reaction. This plus that gives you the 200. So you would have a 20 plus delta H of the reaction is equal to 200. And so 180 would be the number in here. Kilojoules as far as what that space represents. Now, if it asks you if it's endothermic or exothermic, the problem is exothermic, in that the products wind up on the positional energy lower than the reactant energy. Here is a little backwards to that. Here you add up here. This is the delta H of the reverse reaction adds to the heat of reaction is equal to the forward reaction distance here. But when you determine this, you subtract the energy of the activation energy minus the reverse activation energy to get the heat of reaction, and it's positive. Yeah, it's fine. But we're talking about the space between the reactants and the products is what you're interested in. Space between the reactant position and product is plus or minus in reality. But when you work a problem based upon given activation energies, heat of reaction, forward and backwards and so forth, okay, you have to scale left side against the right side. You have to picture this side against this side, or this side against that side. Sum of the left equals sum of the right. Sum of the left equals sum of the right. See the point? And the big picture? Okay. In the same context, we include the energy number in the equation. It'd be A plus B in equilibrium with AB plus your delta H of reaction, showing the exothermic being on the right side, or the product side. Whereas you can write the same kind of equation, or an identical equation, meaning the same, they're identical. Delta H of reaction less than 0 would be a negative number over here. I think I got enough room under here. If an endothermic reaction is being considered and you are heating it, as in the problem specification here, you want to start with writing the endothermic reaction. I'm going to use reactants and products. So in writing this, you'd have reactants plus delta H of the reaction in equilibrium with the products right there. Put it on the seesaw as I'm instructed. And if you heat this issue, now get this, if you heat it, you are disturbing the equilibrium. When I say disturbing the equilibrium, what I mean is the results no longer at equilibrium. You don't have a double arrow. Heating will tilt the reaction to the left. To recover, it has to shift right. Did I catch it? So we have to have a right shift to recover our reactants plus delta H goes to products issue here. I think it's all on here. So we start out in equilibrium. Heat the system. Because the delta H is on the reactant side, we mentally say that absorbs some weight on that side of the seesaw and tilts that way. Like putting another kid on that side of the seesaw. It'll tilt. Now don't mix that up. It tilts left and call it a left shift. Don't call this a left shift. The heating disturbed the equilibrium and tilted the equilibrium in our analysis to the left. That is not a left shift. It has to shift right in order to reestablish the equilibrium. We'll give this a B choice. This, and ask yourselves what happens if we have an endothermic reaction. Reactants, delta H of reaction, it's at equilibrium and goes to products. And in this case, cool. Miss Tiffany, which way will that reaction tilt if I cool it? That's correct. It will tilt to the right because you mentally visualize the delta H being removed when you cool it. It creates a void. A kid got off the seesaw on the left side and it will tilt right. So we're in a condition shown here. Which way will it shift, Monica? To recover its equilibrium. Trying to put a context there. Huh?
To the left.
That's correct. So once you understand the basic idea of what's happening, you're disturbing, causing the tilt right, shift left to recover. The idea is to recover the equilibrium in that it's important to note we have new concentrations of reactant and products. As a matter of fact, the product side went down, the reactant side went up in concentration in order to shift to the left and level. Here's your problem. Given that equation, I want to increase the yield of ammonia. All right. So to increase H3 gas yield, and we want to take into account a concentration, we increase concentrations of reactants. Cause a tilt left shifts right. Because you will be removing delta H's, making the right side of your seesaw lighter and it would tilt left and then on its own shift back to the right. In the right context.